Hi, my name is Emmanuel Excludo and I'm currently taking Physics 2211 at Georgia Tech, and this is my lab report. This lab discusses the constant velocity of the motion of an object and its relation to Newton's second law. Now, this lab discusses three main topics. The first being Newton's second law, which relates the net interaction between system and surroundings to the observed motion of the system. The net force is the vector sum of all the forces acting on the system, and when the net force is zero, the object is assumed to either be in rest or in constant motion of velocity. And constant velocity is a state where the object never speeds up nor slows down. It merely remains in motion at the same rate. The purpose of this lab was to use an object and demonstrate the mentioned constant velocity and Newton's second law in both a lab and real world setting. On the left is an image of a free body diagram of an object, but this free body diagram isn't exactly what we'll be using in the lab because it has two components that we won't be applying. The first is friction, as you see on the left here, and the second is an applied force. The object in the lab is assumed to be at constant velocity or zero net force, thus these two components won't exist as friction isn't applied and force isn't also applied on the right. We have three formulas that we'll be using in this lab. The first is Newton's second law, force equals mass times acceleration. And the other two, the updated velocity formula and the updated position formula, will be discussed on the slide for the computational model. Now here is the experimental model that we use to demonstrate the net force of our object. We use tracker to record this, and as you can see, as the object is moving, there are these little red dots that correspond to the data on the right. There is also a graph showing a downward trend or negative slope relating position and time, and this relates to the Newton's second law. And we'll be comparing this to the computational method in GlowScript as being discussed next. The code was written in Python using GlowScript, and the initial condition of the computational model are shown. In particular, I set the mass of the object to 0.5 as I wanted it to more closely relate to the mass of what I actually used for the lab. I also set the original position of my object to a vector with components 0, 0, and 0, and I set the initial velocity of the object to a vector with components negative 0.75, 0, and 0. And I found this initial velocity by using 2 points in my position time graph gotten from tracker and putting them inside the average velocity equation, thus resulting in the established condition. The delta t was found by me dividing the total length of our video by the number of frames in the video. Now, this is the next section of my computational code. The formulas mentioned before that I discussed. The last two I used in this code, the updated velocity formula and the updated position formula are shown here. The ball has a constant velocity, and thus net force as shown by the Fnet equals vector 0, 0, 0. Now, using this code and the previous tracker data, I was able to create a graph of time versus position for both the experimental and computational model. The graph shows a pretty similar slope for both of them with a negative downward trend as time increases. However, the experimental model is a little bit less consistent than the computational model with time, and I believe this is due to the fact of a little friction as our conditions were not all perfect. However, the data still conveys the same information of position and time having a negative correlation and there being a constant velocity. Now moving on to some follow-up questions. What if we were to flip the axis? Well, the only change to my results would be that the graph would slope upwards instead of downwards. However, it will still indicate the same conclusions, that the model overpredicted for larger time values, suggesting the presence of a frictional force which slowed the object down. To improve the accuracy of our model, in the future we could try using objects with a very low coefficient of friction. Additionally, we could try to factor in the frictional force in our computational model, and both of these approaches will make the model more accurate. We also set the net force equal to 0 in the computational model. However, I don't know for sure whether the net force actually acting on the object was 0. In fact, I know that friction does act on the object, so the net force isn't necessarily zero. It is also very difficult to know how many pushes and pulls add together to give a net force of zero, and all of these factors affect the accuracy of our model. Thank you for your time.